Yeah, thank you, Frauke. Thank you, Florian, and thank you, Annika, for organizing this workshop. And sorry that I can't be there with you in person. I hope you can follow everything. If it doesn't work, then feel free to also interrupt me. So here's a structure. My background is in cognitive science and philosophy of cognitive science. And so I'm mainly interested in the question whether and how AI models could still be useful models in cognitive science. And I have significant worries that they, in their current form, are useful for a cognitive science. I really don't doubt, or I have no idea about whether they are useful for other sciences. So this restricts the scope of my inquiry here, but it fits the workshop, I hope. So I'll talk about ANNs as cognitive models, the fallacy of misplaced concreteness, or makeism, and how to make conceptual progress is one of my key obstacles or issues that I very much invite you to brainstorm with me or help me with. And then I want to suggest that while most of the time artificial neural networks have been compared to humans, which I think came up a lot of times today in other talks too, a new potential way to use them in fruitful ways is to use them as a contrast class. And in my search to make this more concrete, I will use Mary Hess's concept of negative analogies that maybe can be helpful for identifying also when a model doesn't work. Okay, and then I'll go to the summary and conclusion. So I like looking a bit to history. I think it's worth also connecting to the way in which we have traditionally used AI models in this enterprise of studying the mind or cognition. So information processing systems of the kinds that we have and other non-human animals. And here's Herbert Simon, which I think expresses this wonderfully. Even in a world in which there's lots of computers, it still may be important for us to understand human learning. Artificial intelligence has two goals. First, AI is directed towards getting computers to be smart and do smart things so that human beings don't have to do them. And second, and that's the interest here, AI, sometimes called cognitive simulation or information processing in psychology, is also directed at using computers to simulate human beings so that we can find out how humans work and perhaps can help them to be a little better in their work. So that's basically the aim, I think, that AI in the context of cognitive science is supposed to fulfill. And I worry it doesn't fulfill that aim anymore. So currently, we mean a lot of things by AI, right? So here's a non-comprehensive list of different or non-mutually exclusive meanings. And I actually also really like looking to AI as an idea. That is also one way in which people have taken a lot from these tools to develop theories of cognition, and not just, to put it bluntly, toy around with tools. So this idea can, however, also be understood more precisely in different ways. First of all, AI as engineering, as they label it, means intelligence can be recreated in artificial systems. That's the conviction. AI as psychology, in contrast, is the idea that cognition is or can be understood as a form of computation. And I think this is a more interesting way of looking at it when we want to also look to scientific understanding within this context of cognitive science. AI as ideology, humans can be replaced by artificial systems. I think that links to the ethical worries we've spoken about too, and the label AI could also help sell technologies and gain funding would be AI as marketing. So I'm interested in this contrast between AI as engineering and AI as psychology, to put it short. And I'll sometimes also refer to AI as a system, but and also as a subfield, because it's a subfield in cognitive science. Okay, so there's this key problem that I think is a fundamental obstacle if we nowadays want to use AI for psychology or as cognitive models. And that's particularly large language models are really incentivized to mimic the behavioral science that humans typically treat as evidence of aspects of cognition. So Birch thematizes this topic, and Birch is interested in consciousness. So he uses consciousness as this one aspect of cognition. But I think we could also generalize the points towards reasoning, learning, and any other form of cognition, where the system is, of course, built to maximize the mirroring of the patterns of behavior we put up on the table. So just because the LLM shows this behavior, of course, that doesn't tell us whether it's actually a cognitive system or, for example, whether it's conscious as one aspect of that. So he takes this as a reason to doubt that behavior also counts as evidence of consciousness in LLMs, but we usually do take it to count as evidence in humans, right? So we heard one talk this morning that in response to the question whether these models aren't ideal, gave the mapping or their alignment with human data, data on how humans solve reasoning puzzles, for example. And that's evidence for human reasoning that's natural because it is not gained in Birch's sense. But the question here is, can we make the same assumption in the case of AI systems, since they are operating on the principle of mirroring human patterns of behavior and potentially, if you want to call it that way, reasoning. Purely behavioral or linguistic tests here are not really then such trustworthy evidence to begin with. And most of you probably know this branch where in cognitive science, a lot of psychologists now, they use LLMs as replacements for human participants because they pretty well mirror human behavior. But because of this gaming issue that I think is a bad assumption to start out with. So a response would be to look to architectural features of the models in the hope that there's other kinds of resemblance that's not so much behavioral, but rather might resemble activity patterns in the brain, which Carlos mentioned. So in cognitive neuroscience, and here cognitive neuroscience brings methods to mechanistic interpretability researchers. So yeah, Raphael Millet illustrates this in his quote, more than ever, neural networks show promise as cognitive models that can be systematically studied and manipulated by scientists in carefully controlled conditions to enable surrogative reasoning about core aspects of cognition. So high hopes. Yeah, Cameron Buckner adds, at minimum, these models serve as proofs of concept that systems adhering to empiricist constraints can extract certain types of knowledge from certain types of input data. I mean, yeah, but whether that's really revealing anything about humans is still the open question. So we've talked a lot about mechanistic interpretability. So the basic principle in the case of LLM is, again, to look to the kinds of textual features that are being tracked in certain local activation layers in these networks. And so by comparing the performance here of this second step, B, where we have exchanged the node associated with Paris before by Berlin, a Berlin node, we see whether then in the third step, Paris would be restored as an output. So one problem with this approach is, and we discussed it actually last Friday, maybe we can connect to that again, is that it only gives us knowledge of the local function of the networks and not the global cognitive task that they are really computing or fulfilling. And usually, at least if we follow the classical idea of computational level, algorithmic level, and then implementational level, we also want to draw connections between the algorithmic description and a more general description of the what the task of the system actually is and why that task is appropriate for this kind of system, which is the general way in which in cognitive psychology people have been described to approach this issue. And so that's missing here. So it only gives us, maybe this was what Carlos meant, a very local type of knowledge. So more would be needed to give a cognitive analysis of such systems. And then the second issue is it doesn't tell us anything about how humans do it, which I think is one of the key concerns in cognitive science. So here's Chirimuta criticizing exactly this point. The mistake is that of taking the abstractions of science for concrete reality, confusing the model with the target, the map with the territory. So Whitehead's fallacy of misplaced concreteness. Natural philosophers of mind look to science only to tell them about the natures of those objects of research, what's memory, vision, and so on. And their concern is not with how things are with the model, which they take too often to be a transparent, undistorting medium, but in how our brains and cognitive processes. So before you haven't made an analogy or a step from one of these to the other, it would be fallacious to just equate the two. So the fallacy of misplaced concreteness occurs here if an abstraction of a model imposed by a practical necessity is mistaken for discovery about how the brain itself is. So the same worry has also been voiced by cognitive scientists like Iris van Rooij. She calls the mistake of taking the large language model itself as a cognitive system. She calls that makeism, and she puts that in the category of AI as engineering, not AI as psychology. So makeism has three claims. The claim is it is possible to remake cognition computationally. B, if we remake cognition, then we can explain and or understand it. And C, explaining and or understanding cognition requires remaking cognition itself. So they have this wonderful paper. I just want to flag it. I really hope more of you are going to look into it. If you pursue the characterization of LLMs as cognitive systems or systems that have concepts, because if one takes that serious, one also has to deal with intractability issues. So they show premise A is false, because even under idealized conditions, researcher like here, Dr. Ingenia, who in idealized worlds like perfect data, having unlimited computing resources, having access to all possible algorithms, if this researcher would try to learn by empirical simulation study-based observation, what kind of behavior you can get from an AI, it's in an infinitely small of a likelihood that you're gonna actually hit that sub area in that space that actually resembles really human-like learning. Because the assumptions on which this also rests are very abstract about what human cognition actually amounts to. And it's very likely that you're actually missing your target a lot of the times in this reproduction. Okay. Premise C also isn't plausible. So explaining and understanding cognition requires remaking cognition itself. That's a mere assumption currently. There's not really any support, and it's also not the most likely assumption if we look to the alternatives to building cognition. So behavioral experiments, for instance, are still very much done. Brain imaging, as illustrated here on the left, EEG techniques are used. You use neurobiology methods and also other theoretically based methods from computer science. And so there are all these methods that seem to be rather neglected and not connected to the building. but yet we think they are worth doing, and they help us understand what cognition is in the first place and why it's appropriate for certain types of agents like us. Premise B, if we remake cognition, then we can explain and or understand it. So that one also doesn't plausibly seem to follow, because in the case of large language models, we do have the linguistic patterns, but the explanation of why we observe these patterns, it's kind of also distorted and problematized by the gaming problem on the one hand, and on the other hand, it's not inherently connected to one of the key concepts of language use. And we have many of those, and we don't have really an agreement in cognitive science currently about that. So 3 examples would be that the meaning of a term or a concept depends on its causal or referential history. The second one is it's pragmatic and also depends on inferences and communicative intentions of speakers, which are mere postulates in LLMs. We don't have good reason to assume that an LLM itself has the intention to communicate. And on the other hand, that would also put the cart in front of the horse, because this is exactly what we want to explain and is underdetermined by the behavioral data of being able to use language. And the third one would be a semantic correspondence theory, that there's some sort of isomorphic mapping between the semantic content of a representation in the model and categories or sort of kinds out there. And I mean, it's questionable whether we should attribute representations to these models in the first place, more than just calling them simple receptors that just activate whenever a feature is present, which is a correlative notion, but not a semantic notion of content. So Guest and Martin, they similarly raise these concerns. I think they phrase it a bit better than I do, but so their concern is with the usage of the LLM, as we see it here in the picture, as a sort of analogy to brain structures. And you might superficially identify certain looping structures in both kinds of models, but the real issue is for them that the core idea is to treat an ANN as a participant, and to take it off the shelf. So treating models as off the shelf and fine-tuned theory, not as mediators of a theory, means that the computational mechanism available to here M-connectionism means the engineering-based types of artificial neural networks that isn't connected to the theory of connectionism from the 80s. And this is definitionally always the same, regardless of the question, hypothesis, or conclusion, because the model is the same and is just transferred from case study to case study. It's not really used to adjust a theory of cognition. So this is a point to illustrate to you that also in the context of cognitive science, these models really aren't connected to theory. And one issue is that the theories in response aren't developed. So a key worry is, how do we actually make conceptual progress on understanding what cognition is in the first place? And could these models be useful for us to do so? So Margaret Boden, she characterized the use of computer science and computers as tools, not really as means to actually think a toy around, but as such, they are in principle less crucial for cognitive science than computational concepts are that we derive from our activities of tinker-toying around. And here, connectionism has been very fruitful, right? So it helped us to develop hypotheses about how children learn the past tense of English verbs. One of the most prominent uses that Gary Marcus showed. It also helped us to have even a theoretical model of what our visual system might be doing, namely process simple features. The closer you go to the retina, and more complex features, the higher you go up. So things like red is processed lower level, and then things like a whole object, a red ball, is processed at a level higher. Of course, that's an ideal approach, but it's at the connectionist structure gave rise to the hypothesis that we might be doing the same thing. It also helped us to think about what concepts are. We have these two competing paradigms, symbolicism and connectionism. Some people have merged them also, but generally this has been very productive as an opposition to clarify whether we should think of concepts as distributed representations or should we think of concepts as atomic symbols. And so this has been very useful to clarify concepts and enrich our conceptual resources. It also had been helpful to connect the idea that we have concepts to the interaction we might have with the outside world and empiricist views of learning bottom up. But in all these cases, you have a model, and the model itself is not a cognitive agent, but a tool for generating these hypotheses. So it's really a tool for reasoning about a mechanism, and as Stinson phrases it, for a logic of tendencies. And what you do here is you draw inductive inferences from like causes to like effects, but the like already says it. To do that, you need to independently justify that the two mechanisms are relevantly similar in the relevant respects. And I find that just constantly overlooked in the current literature when these models are taken off the shelf, because there are significant disanalogies that are overlooked that, however, maybe could be inspiring to indeed help us formulate more hypotheses. So that leads me to the suggestion that maybe rather than oversimplifying human cognition and disregarding these disanalogies, we could also pay more attention to them and regard ANNs as a contrast class. So Feist gave me this idea. She said something can also be a conceptual resource by virtue of being regarded as interestingly wrong. So negative analogies by Hesse are popular for that. Hesse writes, when I take a collection of billiard balls in random motion as a model for gas, we are not asserting that billiard balls are in all respects like gas particles, for billiard balls are red or white and hard and shiny, and we are not intending to suggest that gas molecules have these properties. So she distinguishes then the negative analogy, which refers to properties of the billiard balls which are not found in molecules, and from the positive analogy. So here we look to the properties we do actually want to ascribe to molecules. In this example, it's motion and impact, and the neutral analogy where we don't know. So properties where we have no idea whether they actually provide positive or negative analogies. And so whether a property really belongs to the negative analogy for Hesse depends also on whether we judge it to be essential to the target system. And this is interesting when we think about human-like cognition. This raises the question, what do we want to assume is actually essential to human cognition? So in Hesse's example, she has this quote, if conservation is not an essential property of fluids, it may be relegated to the negative analogy in the comparison with heat and the rest of the heat fluid model retained as happened with the property of weight. But if conservation is judged to be essential to a fluid model, this negative analogy will be taken to be sufficient to refute the heat fluid model, and the fluid theory will then be said to be false. So just as conservation was eventually treated as essential to fluids, however, and so when we apply this to the case of cognition, one idea would be, but I'm not sure how plausible it is, you tell me, for instance, embodiment has been taking a very central role in cognitive science for characterizing human-like cognition. And so if we take that really to be essential, and it is not shared by LLMs and other cognitive systems, then these systems might just be the wrong kind of model to approach cognition. So actually, they should be taken out of the context of cognitive science is one conclusion, one we might draw from it. But then there's also the case where we don't know whether we might have a negative or a positive analogy, maybe with regards to other factors, things like efficient computation or more functional aspects. And here in this case of the uncertainty, according to Hesse, we could also use this to make new predictions. There's potential to still use these models as fruitful insofar as we don't know whether we're in the case of a positive or a negative analogy. She says in her case, if gases are really like collections of billiard balls, except in regard to the known negative analogy, then from our knowledge of the mechanics of billiard balls, we may be able to make new predictions about the expected behavior of gases. Of course, the predictions may be wrong, but then we shall be led to conclude that we have the wrong model. I think we're not there yet to maybe make that conclusion. I don't want to take away hopes that LLMs could still have some effect or purpose in cognitive science, but I would like to also, maybe you know more about evidence for that claim. And here, if we use it as a contrast class, then I listed features where we can think of it as a negative analogy. So AI does have, in some sense, a sort of efficiency, but it's resource intense, so it's not really efficient in the way that we are, because we have 20 watts in between our ears and we can talk and communicate, and the AI tools or LLMs require massive server cities. Then the functions and tasks are, of course, just external, while most biologists and cognitive scientists would say that we're based on a sort of internal or intrinsic motivation, a drive to survive, as Catherine Ave calls it. Also we are dynamical systems, while LLMs are static. That's required to manipulate them, also for mechanistic interpretability. And so on. So I could follow Carlos's yada yada way of characterizing it. The list probably goes on. It's just that there's more reason. So there's no positive analogy, is a short point. What we could use it for potentially is to actually refine which features are special to us and which ones AI like LLMs don't have, things I didn't hear now. What we shouldn't do, however, is to redefine the cognitive target if it's human-like cognition by taking out the essential features like embodiment, for instance. Okay. One example is learning concepts, but I think I'll refer to it back in the discussion if you're interested. And so I just want to summarize. I've given reasons to not conflate the model with the target when we see recent attempts to use LLMs as models of cognition. We shouldn't mistake the ability to control these models through maybe methods we borrow from cognitive neuroscience, that thus they also help us to develop theories in cognitive neuroscience and cognition, because these models are usually taken off the shelf, aren't inspired by the theories, and also in reverse, they don't modify the theory yet, or I would be happy to hear an example. So one hope I have, but I think I haven't made it plausible very much, is that ANNs, just like connectionism from the 80s, could actually help us to refine the concept of cognition. This would relate back to the idea that they can be helpful for conceptual engineering. Yeah, I certainly have to work out that proposal more, and I'm happy to discuss maybe options about that. Thank you for your attention.